Hi, today we are going to see about radio wave propagation in this video. So in this slide, we introduce radio wave propagation, which describes how electromagnetic waves travel from one point to another through the atmosphere or space. For terrestrial communication, there are two main modes, ground wave propagation and sky wave propagation. Ground wave propagation move along the surface of the Earth following its curvature, while the sky waves are transmitted upward and then bent back to Earth by the ionosphere. These two modes form the basis of most wireless These two modes form the basis of most wireless communication systems. Defining the ground wave. A ground wave, also called a surface wave, travels very close to the Earth's surface during propagation. It is mainly used in long wave and medium wave communication systems. The effectiveness of ground wave propagation depends strongly on the electrical properties of Earth, such as conductivity and permittivity. Because of its stability, ground wave propagation is often used for measuring antenna field strength, especially at frequencies below 1 MHz. Ground wave characteristics and frequency. Ground wave propagation works best at lower frequencies, particularly in the lower frequency and very low frequency bands. As frequency increases, the Earth behaves like a lossy medium, which causes the signal to weaken rapidly. This attenuation limits the efficiency of ground waves because part of the energy is absorbed by the ground. At frequencies above 30 MHz, ground wave propagation becomes almost negligible for long-distance communication. Forward wave tilt and soil interaction. When a radio wave travels parallel to the Earth's surfaces, it experiences a forward wave tilt. This happens because the lower part of the wavefront slows down due to the finite conductivity of the ground. As a result, the wave tilts forward in the direction of propagation. The degree of tilt increases with high frequencies and higher soil resistivity. Certain antennas, like the beverage antenna, are specifically designed to take advantage of this effect for improved signal reception. The ionosphere is a region in the upper atmosphere that is ionized by solar radiation. It contains layers of free electrons and ions that can bend radio waves. This properly makes it extremely important for long distance communication, especially in the higher frequency band. However, the ionosphere is not constant. It changes with the time of day, seasonal variations, and the solar cycle. Mechanism of skywave propagation. In skywave propagation, radio waves are transmitted upward at specific angles towards the ionosphere. Instead of reflecting sharply, the ionosphere gradually bends the wave back towards the Earth. This allows the signal to travel beyond the horizon, sometimes covering thousands of kilometers. For this to work effectively, the frequency must be carefully chosen, low enough to be bent by the ionosphere, but high enough to avoid excessive absorption in the lower layers. Faraday rotation in ionosphere. As radio waves pass through the ionosphere, they interact with the Earth's magnetic field. This interaction causes the polarization of the wave to rotate, a phenomena known as Faraday rotation. The amount of rotation depends on factors like electron density and signal frequency. If the receiving antenna is not aligned with this rotation polarization, it can lead to signal fading and reduced communication quality. Combating Faraday rotation. To reduce the effect of Faraday rotation, circularly polarized antennas are often used. In circular polarization, the wave rotates as it travels, making it less sensitive to polarization changes. For example, helical antennas operating in axial mode can receive signals effectively regardless of rotation. This technique is widely used in satellite communication and deep space systems to maintain a stable signal link. Multipath interference and skip zones. Multipath interference occurs when a receiver gets signal from multiple paths, such as a direct path and a reflected path from the ground or ionosphere. These signals can combine constructively or destructively, causing variation in signal strength known as peaks and nulls. Another important concept is the skip zone, which is the area where neither ground wave nor sky wave signals are received. Understanding these effects is crucial for designing reliable communication systems. To summarize, ground wave propagation provides reliable communication over short distances at low frequencies, but is limited by energy loss in the earth. Skywave propagation, on the other hand, enables long-distance communication by using the ionosphere, through it is affected by solar activity and environmental changes. Both modes influence signal strength and polarization, and careful antenna design, such as using circular polarization, is essential for maintaining efficient communication. Thank you.